All right, let's jump right into this explainer. Today, we're unraveling what is honestly one of the most mind-bending paradoxes in all of computer science and math. We're going to look at something that literally breaks the whole idea that computers can just be infinitely smart. So here's the big question driving our explainer today. Can computers truly know everything about themselves? We're going to explore whether it's actually possible to build, like, an ultimate algorithm that can perfectly predict the behavior of any other program. Think about it for a second. A machine that can look at any code in existence and just know exactly what it's going to do without even having to run it. Sounds like science fiction, right? But hey, before we get deep into the computer code, to really grasp the limits of computation, we first need to prime our brains with a classic self-referential paradox. You know the one? This statement is false. I mean, if it's true, well then it must be false. But if it's false, then it actually must be true. It's like logic is just eating itself. And as you'll see, this exact same pattern is the master key to unlocking our whole computer science mystery. Okay, so the absolutely crucial point here is understanding what we mean by halting. In the computer science world, a program basically does one of two things, right? It either finishes its job and stops, which we call halting, or it gets stuck looping forever, just churning away indefinitely. If you've ever had an app totally freeze up and crash your phone because it got caught in a loop, you know exactly what a program failing to halt looks like. Now, for decades, computer scientists dreamed of creating a master program. The ultimate dream was to build this so-called decider that could look at any piece of code and immediately tell you, hey, this is going to halt, or nope, this is just going to loop forever. Imagine having a magical tool that could perfectly debug any software on Earth before you even press play. It would be a total game changer. So ideally, our master program would work in 3 super simple steps. You take an input, which is basically any program and its data. You feed it in, the machine analyzes the whole thing without actually running that potentially infinite code, and then flawlessly spits out a binary answer for us, halt or loop. Boom, done. All right, so for the sake of argument, let's just pretend we actually built this perfect decider. We'll call it the hypothetical machine, or HM for short. We are going to assume right now, just for a moment, that HM totally exists and works flawlessly. Let's lay out the strict ground rules for HM here. Our flawless HM takes any program, let's just call it P, and its input, I. It evaluates them, and the key here is it never gets stuck itself. HM must absolutely always halt to give us an answer. And it works for any and every program in existence, no exceptions. It is the ultimate infallible oracle. But you know, here is exactly where we introduce the villain of our story. Because if you're building an infallible oracle, you absolutely have to test it against a maliciously designed adversary. So we're going to write a tiny, simple little program called CM, short for the trickster machine, and it is designed specifically to troll our perfect machine, HM. Now, here is the beautifully devious part of how CM works. It basically asks HM for a prediction about what to do next, and then, exactly like a rebellious teenager, it deliberately does the exact opposite of what it was told. I mean, literally, if HM predicts a halt, the trickster loops. If HM predicts a loop, the trickster halts. It's just petty. Let's break down the exact logic of this trickster. CM takes a program, we'll just call it X, as its input. Inside its own code, it uses our perfect machine, HM, as an internal tool. It basically asks HM, hey, what is program X going to do? And the second HM gives its flawless answer, CM executes its core directive. Perfectly contradict whatever brilliant answer HM just gave. So we've set our trap. Now let's ask the real, universe-breaking question. We know CM takes a program as an input, right? But what happens if we feed the trickster into the trickster? Like, what actually happens if X is CM itself? Well, this brings us to the ultimate paradox, CM. We are now asking our totally perfect hypothetical machine, HM, to predict what CM is going to do when it's given its own source code as the input. HM has to look at the trickster and make a definitive, final call. Is it going to halt or is it going to loop? And this right here brilliantly illustrates the inescapable trap. Seriously, think about it. If HM predicts that CM will halt, CM's programming dictates it absolutely must do the opposite, so it loops, meaning HM is wrong. But what if HM predicts that CM will loop? CM immediately halts. So once again, HM is completely wrong. Because CM is just sitting back waiting for HM to make its prediction solely so it can do the exact opposite, HM is completely paralyzed. It's exactly that liar's paradox from the beginning, but hard-coded into computer architecture. HM's entire claim to being perfect is just totally shattered because its prediction directly causes its own failure. There's no way out. What we actually just walked through together is a textbook mathematical proof by contradiction. In Latin, they call it reductio ad absurdum. Basically, to prove something is impossible, you start by assuming it is possible. We accepted the premise that the perfect machine HM existed, we played out the logic, and we watched it spectacularly explode into a massive contradiction. The crazy thing is, the trickster program is incredibly simple to write. Well, if HM exists. But its mere existence forces HM to be wrong. And since HM was defined strictly as an infallible decider, and we know an infallible decider that makes errors is a literal logical impossibility, well, our initial assumption was entirely false. The perfect hypothetical machine mathematically cannot exist. Period. And this isn't just some fun modern thought experiment. This profound limitation of logic was actually discovered by the legendary mathematician and computer scientist Alan Turing, all the way back in 1936. That is way before modern digital computers were even built. Turing conclusively proved that the halting problem is strictly undecidable. No general algorithm can ever be written to correctly solve this problem for all possible program and input pairs. And the reason? It's entirely because of this self-referential trap. Basically, any sufficiently complex system that tries to perfectly predict itself can always be weaponized against itself. So why does all this matter to us? It matters because it reveals a permanent structural barrier in computer science. Logic alone just cannot discover all truths. Think about it. If the halting problem were solvable, we could just write a program to test every number up to infinity and solve impossible math mysteries, like Goldbach's conjecture, just by asking our machine if the program ever halts. But as we've seen, we simply can't. And this whole concept takes us way beyond just computers. Prominent thinkers, like the Nobel Prize-winning physicist Roger Penrose, actually use this exact proof to argue that the human mind cannot merely be an algorithmic Turing machine. The idea is, if computational systems are fundamentally trapped by self-reference, but we humans can step outside the system to understand the paradox, well, there might clearly be a whole lot more to human cognition than pure computation. Which leaves us with a totally fascinating philosophical mystery to walk away with today. Turing showed us exactly where the hard boundary of machine logic lies. But where does ours lie? If perfectly logical machines have hard, mathematically proven limits to their own self-knowledge, do we? It is definitely something to think about the next time you find yourself stuck in a loop.